Uh, my name is Hussein El-Genedy. I am a senior process engineer at Zohr gas field, which is the largest gas field in the Mediterranean in Egypt. I'm a former engineering section head at ProServe Egypt, and here is my email if anyone would like to contact me for any clarification or any technical question or anything needed. Okay, this will be our index for today. First, we will start to take an introduction about the oil and gas itself. What is the oil and gas? After that, we are going to speak about the composition of oil, crude oil, and the types of crude oil. After that, the grades of the crude oil. What are the grades, and how we know which grade is good or bad? What is petroleum refining? After that, we are going to talk about gas, natural gas composition and types, phase behavior, natural gas properties, and gas contaminants. After that, we are talking about an overview of gas processing. As I mentioned, some of information will be maybe repeated, but excuse me, it's just an introduction, not a detailed course about the oil and gas processing. Okay. The oil and gas, introduction to oil and gas. Oil and gas are a mixture of naturally occurring hydrocarbon compounds. Hydrocarbon compounds are mainly compounds combined of carbon and hydrogen. And these compounds are found in rocks, some sort of rocks, which has been formed thousands or maybe millions of years by the heat or the pressure, which turn the organic compounds or organic matters, such like living organism or organisms or living animals, to an oil and gas. The oil and gas are found in reservoirs. This is a typical reservoir. There is a lot of types of reservoirs, but this is a typical one. And we are not going today to talk about the types and the kinds of all reservoirs, but this is a typical reservoir. And some reservoirs are found on shore, which means inland, on land, and the others are found under the sea bed, which is called offshore reservoirs. The reservoirs mainly, this is associated gas reservoir, consists of water and oil and gas. The compounds or the phases are mainly must be like that because of the density of the water is higher than the oil and the gas as well. After that, the oil compositions and types. In general speaking, there are two types of oil: conventional oils, which is found in a form of vertical shafts that like a bowl, like that we showed here in the previous slide. Just a vertical, you have to drill only the well and start sucking the oil from the reservoir. And there is other unconventional oils which need special technologies and need more cost, and it's not easy to extract oil from unconventional oil sources, which is like oil sand and shale oil and heavy oil. The next picture will describe the conventional and unconventional oil and gas wells. Look at this side. This is conventional non-associated gas. We will know what is non-associated and associated in the next slides. This is conventional. It's easy to extract the gas. Just you have to drill the well and extract the gas from the reservoir. And there is also a conventional associated gas well reservoir, which you can easily extract the gas and oil. Here down is the sand stone, which is tight gas sand or sandstone, which is unconventional oil or gas well. You have to make a directional drilling, maybe horizontal drilling, to extract this oil or gas, which is more costly and is not easy to extract. Okay. The composition of oil, the crude oil is a multi-component mixture, is consisting of about 108 compounds. And the typical composition of crude oil is about 90 to 98 hydrocarbons, 0.2 to 3.5 nitrogen and oxygen. And when we say nitrogen and oxygen, it's not pure nitrogen and oxygen, it's nitrogen compounds and oxygen compounds, such like alcohols and esters and ethers maybe. Also the sulfur exist, maybe or maybe not exist in the crude oil. The percentage is 0.5 to 6%. And also when we mention sulfur, we are mentioning sulfur compounds, which like H2S, mercaptans, and so on. So the composition of oil in mainly, as we mentioned, hydrocarbon, and there is a lot of types of hydrocarbon, such like the paraffins, olefins, naphthens, and aromatics. And when we start to extract an oil from any well, we have to make something called PONA analysis. PONA analysis just telling us how much content of paraffins, olefins, naphthens, and aromatics exist in the oil which we are extracting. And there is other non-hydrocarbon compounds, such as sulfur compounds, nitrogen compounds, oxygen compounds, and some metal like nickel, vanadium, and so on. Okay, let's talk about paraffins. Paraffins are also known as alkanes, and they are saturated compounds. And when we say saturated, it means it has only a single bond, no double bond exists in the compound. The paraffins are like methane, ethane, pentane, and this is a straight chain compound with no double bond, saturated compound. And there is also isoparaffins, which is a branched paraffins, such like this one. When this is branched paraffin, it's called isoparaffin. And the difference between the paraffins and isoparaffins in the properties, physical properties, the composition or the chemical construction or structure is the same hydrocarbon, same carbon atoms and same hydrogen atoms, but it's the difference in the physical properties. This is an example. The pentane boiling point is 36, but the other isomers of the pentane are different in the boiling point, which is very significant. We have any. We must consider this when we are dealing with the isoparaffins. It's changing in the physical properties. The other compounds exist in the crude oils are the olefins, but generally the olefins are not presenting in the crude oil as a crude at the beginning in the well. However, they are formed during the processing, like the dehydrogenation of the paraffins and naphthens. And the olefins are not saturated compounds because they have a double bond. They are not saturated and are going to form a lot of compounds and reactive. They form polymers. They are making a lot of problems in the refinery when they are existing. The other type of compounds are the naphthenes, which are cycloparaffins. It's also non-saturated. It's also saturated, which have single bonds, no double bonds. And also they are not reactive and naturally exist in the crude oil. The last one is the aromatics. Aromatics are non-saturated compounds, and it's very important in the refinery to increase the aromatics content in the final products because they increase the octane number of the fuels, such like gasoline and kerosene and so on. So the aromatics are very important in the refinery. The examples of about aromatics is benzene, toluene, and xylene, which are the most popular compounds, aromatic compounds exist in the oil and the gas. The grades of crude oil. The crude oil is categorized based on two things. One thing is the density, which we refer here to the API gravity, and there is a formula to calculate the API gravity from the specific gravity of the crude oil, and also the sulfur content. Let's look at this graph here. There is the grades of crude oil based on their sulfur content and the API gravity. As the API gravity increases, the density of the oil decreases. And as the API decreases, the density of the oil increase. And whenever the API gravity number is high, which means crude oil is more light and more good for the refinery, and no need for more processing or a lot of processing to extract the valuable components from. And the grades here, like the Mexican oil, the Kuwaiti oil, the UAE, and the Brent and the Texas oil, it's all depends on the gravity and sulfur content. We can see here the Brent and the Texas oil are most valuable crude oil. That's why the price is higher, because they are light in the API gravity. Their density is light and the sulfur content is low, which is means they are sweet crude oils, not sour. Okay. Here's a good picture describing the difference between the lower API gravity and the higher API gravity. You can see that the lower API gravity means high density, and the crude or the oil is like that, and the higher API gravity means low density, which means the crude is more light and visible. Okay. As we mentioned, the less refining a crude required, when the crude required less refining when it is light and have no sulfur content or a little sulfur content. That's why it's considered less refining required. So this means its value will increase when it's need any small amount of processing, not very large amount of processing, not complicated process to refine the crude oil. This means it's valuable and its price is high, as we mentioned before. Also, when the sulfur content is high, this means it's difficult to refine the crude oil and it's need further processing, which means its price will reduce because of the processing required. Okay. What is petroleum refining? When we talk about oil and gas processing, there is two types of oil processing. Oil processing, one is preliminary oil processing. It's done in maybe in the site or at the platform, which is maybe desalting or heater treater as a fill, just to remove the salt, to remove the water if it exists. This is a preliminary processing. But after that, to take the valuable products from the crude oil, you have to refine the crude oil. So what is a petroleum refining? The petroleum refining has one goal, is to convert as much as of a barrel of crude oil into a transportation fuels. This is the goal of the refinery, is to convert as much of a barrel of crude oil into a transportation fuel. And transportation fuels have a boiling point ranging from 25 to 350 degrees Celsius. Okay. So let's check here how much transportation fuels are taken from the 1 barrel of oil. The most of crude oil is converted to gasoline. This barrel is 42 gallons or 159 liters, and these numbers are on gallons. Okay, these numbers are gallons. So from 42 gallons, there is around 20 gallons are converted to gasoline, and then about 10 gallons are converted to diesel. and some other products like fuel oil, like asphalt, like these products like coke are around 7 gallons, and there is heavy oil, LPG, jet fuel. Jet fuel is around 4 gallons of each 42 gallons. Let's check this small video about the barrel of oil and the final product. Around 40% is gasoline and 25% is distillates, which are fuel for trucks, trains, and heaters. And kerosene and jet fuel, around 10% of the crude oil barrel, which is very valuable. And then about 22% is residual fuel, which is also used in the tankers and the power plants. And about 1.5 of the barrel, 20% is used as propane, naphtha, asphalt, and so on. So again, what is petroleum refining? Petroleum refining is about a combination of physical and chemical process. Can anyone tell me what is the difference between physical and chemical process? I'm waiting for your answers.
Can you answer this verbal, or you need to write?
Again, the voice is not clear. Can you repeat?
Can you hear me now? No?
Can you speak English? Does anyone know what is the difference between physical and chemical process?
Can I say?
I'm waiting for your answer.
Can I say?
Yeah, go ahead.
In the physical processes, we change the physical properties like heat, density, or like physical properties. But in the chemical processes, we change the chemical structure of the compounds. And or reacts with other compounds.
You are very close, but let's say that in the physical process, we are not changing the properties of the matter. We are not changing the properties of the matter. But in the chemical process, we are changing the structure of the matter, like the crude oil, like the alkylation, for example, process. We are changing the properties of the matter, changing the matter from A to B. This is a chemical process. But in the physical process, we are not changing the properties of the compounds or the components. Okay. So the dominant physical process in the refinery, or the main process in any refinery, is the distillation process. And this is the most important process in the refinery, because it's enable separation of light components from heavier components, and it's about 70% of the refinery operation is the distillation process. And chemical processes such like alkylation and isomerization, and it's also very important in the refinery, because they are their value comes when you are going to increase the yield of the fuels such like gasoline or kerosene, or when you are going to increase the octane number for the fuel. As we mentioned, the aromatics are very valuable when it comes to blending and increasing the octane number. There is the value of the chemical processes in the refinery. And also there is a lot of other processes such like desulfurization, dehydrogenation. It's also required to remove the contaminants of the crude oil. Here when it comes to a chemical process, using the catalyst, using so on, this is the importance of the chemical process in the refinery. Okay, let's move on. Here is a typical distillation tower in the refinery. As we mentioned, this is the most important process in the refinery, which consists only about heating and a distillation column, and it based on this a variation in the boiling point of the components between the gases and the gasoline, naphtha, and kerosene. There is a different boiling point at which each component or each group of components boils. And this is the main concept of the distillation tower, is separate the components based on their boiling point. And from this, the components, each component is going for a further processing and further maybe reforming or blending. Okay. If anyone has any question at any time, please raise your hand or just say it, no problem. Okay. This is a typical refinery. The most important, as we said, is atmospheric distillation and vacuum distillation. And after that, it comes to catalytic isomerization. Isomerization is, as we mentioned, changing the physical properties of the matter, changing the structure from paraffins to isoparaffins, for example. And this allow for a better octane number for the gasoline and the other planes. Hydrodesulfurization, for example, it's used to remove the sulfur compounds from the crude oil. And then catalytic hydrocracking, it's used to crack the heavier components into small components, which are valuable to the refinery and the products. All the cracking operations, such like the hydrocracking or catalytic cracking or thermal cracking, are the main purpose of them is to crack the higher or the heavy components into light components, which are very valuable when it comes to the octane number and the gasoline blending and the other products blending. And there is a lot of processes which we are not going to talk about today because it's need more details and a lot of slides. But just as this is an overview of the processes. If anyone has any question, please say it, and let me check if we can answer your question. No one?
I don't have any questions, sir, right now.
Okay. Is it clear for everyone what we are talking about? If there anything is confusing, please let me know. And if there's anything is not clear, please let me know. Okay. This is, as we mentioned, a process overview of the refinery, crude oil refinery. Okay. Let's move on to the gas composition and the gas types. The gas is mainly, as we mentioned, is hydrocarbon mixtures. But the difference between gas and oil, the gas is very light. It consists about from C1 to C7 plus components, no more. And it's very easy to process the gas compared to the oil. Okay, and the typical composition of the natural gas, if ethane around 94%, ethane around 4%, and propane 0.5, butane 0.15, and butane. This composition differs from one reservoir to another, from one gas to another. But mainly the natural gas is methane. Mainly the natural gas is methane. Around 90% plus of natural gas is methane. Okay. There is two types of natural gas when we are talking about the reservoir. There is two types of reservoirs of natural gas. The first one is the associated gas, and the second is the non-associated gas. The associated gas exists with the crude oil. As we saw in the first picture, the reservoir consists of water, and above the water becomes the oil, above the oil becomes the gas. This reservoir or this gas at this situation is called associated gas because it's associated with the oil in the reservoir. Okay. The other type of gas is non-associated gas, which is a gas reservoir only. There is no oil in the reservoir, which at this point it's called as non-associated gas. We may have water in the reservoir, but no oil. At this point, we call this reservoir non-associated gas. There is another definition for the rich gas. The rich gas means the gas contains heavier hydrocarbons. Heavy hydrocarbons, which is around C5 plus, not more than this C5 plus, which is in the normal conditions of pressure and temperature or liquid. Okay. Another definition: natural gas liquids, which are as a component, are separated in the normal temperature, the ambient temperature and pressure, are separated as liquids from the natural gas. And we will talk about the natural gas liquids in brief in seconds. Okay. And the natural gas liquids are very important because they are blended to the gasoline and the condensate and increase the octane number and the valuability of the crude oil in the refinery. Okay. Next. There is some important definitions. You have to differentiate between those definitions to better understand what we are talking about. There is one thing called NGLs, which is natural gas liquids, and this is, as we mentioned, the liquids which are separated from the gas in the ambient pressure and temperature becomes any liquid. And so there is two grades from the NGLs, the Y grade and the X grade. The difference between them is the Y grade contains ethane, but the X grade doesn't contain ethane. And there is another definition, which is LNG. There is a difference between NGL and LNG. LNG is the liquefied natural gas, which is mainly methane, and it's liquefied at minus 162 degrees Celsius. After liquefaction, it's exported or shipped by tankers, and then we convert it to gas again. It's liquefied just to be easy for transportation, to easy for export. Here is a small question, and I need your answers about it. Do you know what is the volume of 1 cubic meter LNG when it converted to a gas? How will be 1 cubic meter of LNG when it's converted to a gas? Can anyone answer this?
So 23.643.
Thank you, but sorry, is a wrong answer. Again the question. If I have 1 cubic meter of LNG, 1 cubic meter of LNG, how much will be the volume when I convert it to a gas state again? Can anyone tell me?
I think it's about 600.
Yes, correct. It's about 600. Can you imagine 1 cubic meter of LNG can be converted to a 600 cubic meter of gas when it's converted to a gas state? Okay. The other definition is the LPG, which is liquefied petroleum gas. The LPG, which we are using in cooking and heating inside the cylinders, this is the LPG. It's mainly consists of C3 and C4, propane and butane. And the final definition is the condensate, which is the C5+, and this is very valuable in the refinery because it's going to be blended with the crude oil and the other light products. Okay, any question? No. Let's move on. There is a very important curve to know about, which is the phase behavior of the natural gas. The phase behavior of the natural gas is a relation between the pressure, temperature, and volume for each gas, and it's called a BVT diagram, or phase behavior envelope. And this phase behavior changing from one gas to another, from one reservoir to another. There is one phase envelope for each gas, different from the other gases. Okay, let's take a look about the phase envelope of the gas. Here is the diagram of the phase envelope of one gas, and here is the temperature, here is the pressure. We have some important things to know about the phase envelope or about this diagram. The first one is the dew point curve, and the second one is the bubble point curve, and the pre-condenser and pre-condenser, and the critical point, the retrograde. First of all, the dew point curve. Here is the definition for the dew point curve. This curve separates the pure gas from the two-phase region. When we go back to this phase envelope, we can find that here is the gas only. There is no liquid exists at this region. And here is the liquid only. There is no gas exists at this region. And at this point, inside the dew point of the bubble point curve, here at this area, at this region, it's called two-phase region, at which the gas and liquid can coexist with any different person. So the dew point curve, this is the differentiation between the gas region and the liquid region. And the dew point for each gas at any certain pressure or as a definition, the dew point at certain pressure is the first temperature at which the liquid starts to appear. In the opposite side here, we can find the bubble point curve, which also a differentiation between the liquid and the two-phase regions. And also, as we mentioned, the bubble point bubble point pressure at a certain temperature, or bubble point temperature at certain temperature, is the point at which the first gas appears in the mixture. Okay, the first gas appears in the mixture. We have also an important definition. This is Crichton-Therm here, which is the maximum temperature at which gas and liquid can coexist. Maximum temperature at which gas and liquid can coexist. And above this temperature here, there will be no liquid, no matter what was the pressure. Above this temperature, there will be no liquid, no matter what the pressure. On the other hand, here's the Crichton bar, at which is the highest pressure at which gas and liquid can coexist together. And also above this pressure, there will be no gas, no matter what was the temperature. Only will be a liquid above this point. And the critical point is the point at which the dew point and bubble point will meet, which is a critical point. There is an important definition here called the retrograde region. The retrograde region, simply, let's take an example. Here, the formation of liquid hydrocarbons in a gas reservoir as a pressure decreases. Let's take a look here. When we are the reservoir at this point and we start to decrease the pressure, at isothermal condition. Isothermal condition means the temperature is constant. Let's make an imaginary line here, means the temperature is constant at this point, and start decreasing the pressure, go like this. The liquid will start to appear. But in the normal operation, when we decrease the pressure, what will happen to the gas? Can anyone answer? If I have some gas and decrease the pressure, what will happen? Anyone? If I have some gas at certain pressure and decrease the pressure of the gas, what will happen at this condition? Isothermal container contains some gas and the pressure decrease.
It will condensate.
Condensation.
When the pressure decrease, it will condense or vaporize?
Condense.
No, it will vaporize. When I have some gas vapor, it's already vapor, and I reduce the pressure. When reducing the pressure, I increase the distances between the atoms. Can you please mute your mic? Okay, when I have some gas in a container, okay, and decrease the pressure. Decreasing the pressure means the distance between the atoms will increase, and this will never condense. It will vaporize or continue to be at the same state, which is gas. But this region is called retrograde because this is a reverse of what happens in the nature. Because when I decrease the pressure here, the liquid will start to appear, or a condensation happens, which is not normal in the normal life or in the nature. That's why this region is called retrograde. Okay, so it's okay. Did you understand or not? Anyone?
Yes, clear.
Clear? Okay. So that's why they call this region retrograde, because it's not like the nature behavior. Okay. Yes. Okay. So this is the definitions we already mentioned: bubble point curve and the dew point, critical point at which the curves meet, bubble point and dew point curve meet, Crichton term and Crichton bar retrograde. Okay, all definitions are done. Okay. So let's talk about the natural gas properties. The most important, one of the most important properties is the gas specific gravity. As you mentioned, the gas consists of a lot of components, and we cannot assume the gas density or specific gravity, but only we can calculate it. So we can calculate it by multiplying the summation of the mole fractions, each mole fraction by the molecular weight of each component, and divided by the molecular weight of the air, which is 29 or 28.97. Here is an example for calculating the specific gravity of a natural gas found in some reservoir. Here, the gas consists about 87% of C1, 0.084 of C2, 0.023 of C3, and CO2 0.016, and H2S 0.006. This is mole fraction. This is mole fraction, not percentage. Okay, how do we calculate the specific gravity? We calculate the specific gravity by multiplying each mole fraction with the molecular weight of the component and take the summation of all and divide it by the molecular weight of the air, such like this. So the gas gravity will be the mole fraction multiplied by each molecular weight of each component, like this, and divided by 29, which will be 0.634. That's why that's how we calculate the specific gravity of any gas, of any natural gas exists. Okay. The second most important property is the Z factor, or the deviation, gas deviation factor. The deviation factor is generally or simply, it measures how the real gas deviates from the ideality. We know there is no ideal gas in the real life. So the Z factor is a measure of how the real gas deviates from the ideal gas. And we can calculate the Z factor from the charts, such like this one, by calculating the pseudo critical pressure and pseudo critical temperature from the summation also of the mole fraction. You know, the critical pressure for each component is known. For methane, for example, for methane is known, for ethane is known, but we cannot calculate the critical pressure for a natural gas mixture, or we cannot assume, I mean. So we can calculate it by also multiplying the mole fraction of each component by its critical pressure, and also the critical temperature is the same. After that, we can get the reduced pressure and temperature based on the operating pressure and temperature of the gas. This will allow us to enter the curve and define the Z factor of the gas. So this is just calculations to define the Z factor of the gas, or how this gas deviates from the ideal gas in properties or in any characteristics of the gas. And there is also any correlations and softwares to obtain the critical pressure and temperature for the mixture. And it's not not mentioned here, but there is a lot of correlation and softwares to calculate the critical pressure and temperature. And if you are using Aspen HYSYS to Aspen Plus, it will be calculated automatically. Okay. And this is the most important properties: the density or specific gravity of the gas and the Z factor. No need to mention, there is a lot of other properties, but we are not going to mention here due to the time limitation. But those are the most important properties of the natural gas. Okay, let's move on. What is the gas processing? Okay, the gas processing or processes are can be broken into two major categories. The first one is to remove the contaminants of the natural gas, because the natural gas comes with some contaminants we will mention in a while. So we need to remove those contaminants from the natural gas to be able to be sold in the market. And the other thing is to remove the natural gas liquids or the condensate exist in the natural gas, because they are any valuable compounds or valuable products can be sold separately, or can be added value to the gas plant. So there is two types: removing of the contaminants or removing of the liquids, such as like NGLs or condensate. Okay, what are the contaminants of the natural gas? The main contaminants are the water, hydrogen sulfide, and non-combustible inert gases, such like the CO2 and nitrogen. We will talk about each one in brief here. So, and there is other contaminants, maybe or maybe not exist, such like solids, oxygen, mercury, helium, and norm, which is naturally occurring radioactive materials. Maybe exists or maybe not. And also the hydrogen sulfide maybe exists and maybe not. And by the way, when the hydrogen sulfide exists in the gas, we call this gas sour gas. And when there is no hydrogen sulfide in the gas, we call this gas a sweet gas. Okay. What are the problems of the water? What problems can water make to our gas? The first and the major problem is the hydrate formation problem. The hydrate formation or hydrate are something like ice are formed in the pipelines at specific pressure, mainly high pressure and low temperature, and cause a lot of problems, such like blocking of the pipeline. They reduce the volume of the pipeline and also reduce the amount allowing you not to produce or to take all production from the pipeline. As the size of the pipeline will reduce, and you cannot take all the production from the pipeline. It will be a limited volume of the pipeline, and also the water cause corrosion to the pipeline, and as we mentioned, blockage. This is a picture of the hydrate formation. Maybe not a total blockage, but as I mentioned, it will reduce the volume of the pipe, and you cannot make use of the whole volume of the pipe for the production. Okay, and this also is a picture for the corrosion caused by water. Next is the hydrogen sulfide. Why we need to remove the hydrogen sulfide from the gas? Because it's a toxic gas and corrosive gas, and also we need to remove the hydrogen sulfide because we need to keep our environment clean and safe. Maybe some of you know, or some don't know, the hydrogen sulfide is very toxic gas. Let's take a quick overview about what will happen if you expose to H2S. Those numbers are in ppm, part per million. It's a very small amount. The H2S has the odor of rotten egg up to 10 ppm. After that, you cannot, or you never smell the H2S. It will be a silent killer above the 10 ppm. From 10 or 20 to 100 ppm, it will cause irritation to the eyes, and the breathing will not be very well. Above the 100 ppm, there will be severe irritation of the eyes, and the cough, and there is breathing will be very, very hard. Above the 25 ppm, it will be very difficult to breathe, and maybe you lose your coordination or lost your consciousness. Above the 500 ppm, it will be very struggling to breathe, and you may be fainted or lose your consciousness. Above 750 ppm, I am talking about ppm, which is very small amount. It will be death in few minutes or moments. Depends on the body and depends on the wind. Depends on a lot of things. But above 750 ppm, it will be a killer. It will be a silent killer. That's why it's very important when you deal with a sour gas or a sour gas plant. It will be a very tough safety regulations and safety equipment must be used. Okay, this also, as we mentioned, because it's very corrosive to the pipelines. This is a corrosive, corroded pipeline by the H2S. Okay, let's check the chat. What is the abbreviation for BPM? BPM is part per million. Part per million. It's one part per million part. 1 part per million one. The 1% is 1 per 10,000 ppm. Okay, so the 1 ppm is 1 per million. 1 per million. 1 divided to million. Okay, which is very, very small. Okay, the other contaminants are the non-combustible inert gases, such like the CO2 and the nitrogen. Why we need to remove them? Because they have no value. They reduce the heating value of the gas, and also they take valuable space in the pipeline. Sometimes the CO2, when get mixed with water, becomes very corrosive to the pipeline and equipment. Okay. Let's take an overview about the gas plant in brief. The gas plant, we have the fluid pipelines, such as gas pipelines comes from different wells or gathering gas from some wells are collected to a gas header. And the header is a bigger pipeline which collect the gas from different pipelines. Okay. After that, the first thing in the plant is the slag catcher. Slag catcher is a separation process we will talk about in brief, at which the gas is separated from liquid. After that, the gas is, if the gas is sour, it went to sweetening or acid gas removal, sweetening process. And after that, the treated gas from sweetening is entering the dehydration process or water removal process. After dehydration, the gas is called a sales gas, and it went to the metering station, at which we count the gas being sold. Okay. From the sweetening process, we have a byproduct, which is H2S extracted from the gas. The H2S is sent to an SRU unit, which is sulfur recovery unit, at which we can recover the sulfur from H2S and can be sold in the market also. The liquid portion here is sent to a further separation, because when we are talking about liquid is almost condensate and water and MEG. We will talk about MEG in brief in a moment. Okay, so the liquids are going to separation. Mainly the condensate is sent to stabilization, condensate stabilization, and to metering to be sold as stabilized condensate. The water is sent to important units are SWS and MRU. SWS is sour water stripping, and MRU is MEG recovery unit, at which we recover the MEG. And the SWS is produce a waste water without H2S, which is sent to maybe be reused in the plant or sent to dispose. Okay. First unit in the plant is the slag catcher. What is the importance of the slag catcher? Slag catcher is acting like a slug control. Sometimes due to choke up and choke downs of the well, we receive slugs of water or slugs of liquid, which we cannot handle with normal separation. So it's required to use some separator called slag catcher, which is finger types like this. Separator with finger types can handle the high amount of liquid coming from the wells. And also, it is the first defense line when it comes to liquids and slag control. It is the first defense line. So when we expecting, when we are using, when we are separating gas from liquid, we have to use something like that. Especially when we expect different amount of liquids changing from time to another, and especially when the sea lines or the fluid pipelines are far from the plant. For example, in our plant, in Zohr gas plant, the wells are 200 kilometers far from the plant. 200 kilometers. So it's a very long distance. So sometimes liquid is coming in slugs, so we need to use the slug catcher at the first. Okay, and also it helps in separating the liquid from the gas. Let's check this small video about the slug catcher to understand how the separation occur in the slug catcher. Okay. Here is a mixture of the liquid and gas is entering the slug catcher and moving like that. This is the first separation as a separator. The liquid goes down and the gas goes up through these pipelines. As you can see, there is still also some condensate here or some liquid with the gas. So it comes to another stage of separation at which the liquid condensate goes down by gravity This is the benefit of the fingers, and the gases goes also above again and move to a separate pipeline like this. So this is the importance of the fingers. This is called fingers, and the separation is done by gravity. Liquids goes down and gas goes up. This is the idea of slug catcher. As you know, as you can see here, the gas is above here, it's collecting and sending to a processing, and the liquid separated from the gas is sent to the other separation and condensate stabilization. Okay. The next process is the sweetening unit or the acid gas removal unit. The acid gas removal unit is the main purpose is to remove the H2S, but sometimes CO2 is removed with the H2S based on the solvent selected or based on the process selected. The most common sweetening process is the amine sweetening process. The amine sweetening process, at which it consists about the absorber and the regenerator. The absorber, in which there is a contact between the gas and the amine suck or absorb the H2S from the gas and then sent to regeneration to separate the acid gas from the amine, and the amine is resent again to the cycle, and the H2S is going to SRU, and from above here, the gas, sweet gas, is taken from the absorber to be sent for further processing and dehydration. Can anyone tell me why it's important to make the sweetening process before the dehydration process? Anyone know why we are make the sweetening process before the dehydration process? Anyone? No, it's protect pipeline from corrosion. We already have pipelines at which the product is coming maybe a long distance, as mentioned. This is not the main purpose.
Because on the sweetened gas treatment, there is a mixture of water and amine. So I think it's not possible to do the data.
Yeah, you are very close, because in the sweetening process, can you turn off the mic, please? Because in the sweetening process, we are using water. We are already using water. The amine solution is not 100% amine. It's already consists of water, and there is also a makeup water. So we are putting water into the gas. So we cannot make the dehydration before the gas, remove the water before the sweetening, and then re-add water again. So the proper sorting of the operation must be sweetening after that dehydration, because there is water is being inserted in the sweetening process. Okay. The dehydration process is mainly the same the sweetening process, but with different solvent. Here we are using glycol. As a sweetening, we are using amine. But there is two different types of operations in the dehydration. Some one of them is the absorption. Absorption is done by glycol, and some other operation is the adsorption, which is done by solid desiccant, such like the silica gel or a molecular sieve. The purpose of the dehydration process is to remove the water and dew point control. As we know, the dew point of the gas differs based on the amount of water exists on the gas. When the amount of water decreases, the dew point of the gas decreases, which is very important, because the hydrate formation temperature is also based on the dew point and the water content of the gas. And when we reduce the dew point, we protect the gas from hydrate formation. We protect the gas from hydrate formation. This is the main purpose of the dehydration unit. Okay. This is the other type of dehydration unit, dehydration, which is by adsorption by molecular sieves and or silica gel. Okay. After that, it comes to metering. Metering is metering station is just assemble or assembly of valves and flow meters in a certain way, and instrumentation only also. The importance of metering station is that you have to calculate or to know how much gas you reduced or sell or receive from your company to the other company. That's why it's important to install the metering station in the gas plant. It's important in selling or purchasing the product. Okay. And there is also metering for, as there is metering for gas, there is also metering for the stabilized condensate. Okay. After that, it comes to the SRU or sulfur recovery unit. The H2S out from the sweet unit is sent to the sulfur recovery unit, which is the main or the most common process of sulfur recovery unit is the Claus unit, which is consists of a thermal reaction, and after that a catalytic reaction, at which the H2S is converted to a liquid sulfur, and after that we can convert it to solid sulfur. Okay, and it is important also for the environment. The SRU unit is very important for the environment, and at the current recently there is also some unit called a tail gas treatment unit, because the conversion inside the SRU is not 100%. There is a residual gas or tail gas. Recently, a lot of plants are installing a TGT unit or a tail gas treatment unit to increase the recovery of the sulfur from the H2S and minimize the emission. Okay. As we mentioned, liquid coming from the slag catcher or separation or the well consists of oil and water, and sometimes MEG. When we are talking about MEG, the MEG is monoethylene glycol. Some plants are using monoethylene glycol, inject the MEG into the wells to inhibit the hydrate formation. And after injecting the MEG into the well streams, it comes to the to the plant, to the processing plant for recovery. We recover MEG from the liquid. So here in the separation, we are separating the liquid into water and MEG together, because water is mixed with MEG, and oil. Oil is mainly the condensate, which is sent to the stabilization. And also there will be some gases went out from our stream. It's sent to a compressor and after that sent to the sweetening again. Okay. From the separation, we take the condensate to the stabilization unit, at which we can produce the stabilized condensate. Stabilized condensate, the main purpose of the stabilization is to remove the H2S and remove the lighter components from the condensate. Okay, so we remove the acid gas, we adjust the RVP, which is the red vapor pressure. Okay, and we also have to meet the specs. The specs for the liquid is H2S is 10 ppm, and the RVP is up to 15 psi. Depends on the either it's a summer or winter. In summer it should be a little lower, maybe 8, and in winter it should be up to 15. This as the red vapor pressure increase, as the lighter components increase, and this allow in the winter, especially allow the engine to start more easily. The stabilization process is just like the fractionation or the distillation. It's a heating process and then separation based on the boiling point. Okay, this is a very simple BFT of the stabilization process. After that, or the last process in the which medium is used in the exchanger. There is a lot of mediums we can use in the exchanger. Here we can, if there is no product, we can use the product already instead of using a cooler. Here we can use the product to be exchanged with the inlet stream, or we can use steam. For example, at our plant in Zohr gas field, we are using steam. Some other plants are using hot oil instead of the steam. So there is a lot of variants you can use. We can use in the exchange. Okay. So, but the most economical option is to use the product, the hot product, to be exchanged with the feed. Okay, this will reduce the heating duty and reduce utilities such as like steam or hot oil. Last operation in our plant will be the SWS, sour water stripping. Sour water stripping is more or less like the stabilization, but at which we are using, we are removing H2S and lighter component from the water, from the sour water, and then we can reuse it or send it to disposal. Okay, SWS is more or less very like the stabilization process. Excuse me. It's very similar to the stabilization process. Okay. Last operation is the MRU, which is MEG recovery unit. As we mentioned, monoethylene glycol is being injected to the wells for any hydrate inhibition, and after that we recover the MEG because it's very expensive. So we recover the MEG to re-injected again in the system, and this process consists also of heating and fractionation. But there is most important, the most important is this process must be done under vacuum. Can anyone tell me why this process must be done under vacuum? This is last question. Can anyone answer why this process must be done under vacuum? Okay, I will answer. As we know, when we reduce the pressure, what will happen to the boiling point of the component when we reduce the pressure?
It also reduce.
Yeah, the boiling point reduce. So when we are fractionating the MEG, we are using vacuum to reduce the boiling point of the MEG. Why we are doing this? Because the degradation temperature of the MRU of the MEG is very close to the boiling point. The degradation temperature means the MEG will reach a point at which it will not be, it cannot be reused. It will be degraded. It will not be valuable anymore. Cannot be recovered. So the degradation temperature is around for the monoethylene glycol 165. And the boiling point is around 135. That's why we are using vacuum to reduce the boiling point up to 110. To cover all the operation upsets. Some operator may forget the steam flow for some time, which will increase temperature and reaches degradation temperature, and we will lose all the MEG, which is very costly and very valuable component in the plant. That's why we have to make this process under vacuum. Okay, and also there is some salt recovery process done in the MRU because the fluid coming from the pipelines must have some salts and some vessels, sands or solid items. And also because sometimes when the water comes from the reservoir, it's become very salty, and we have to remove this salt from the to be re-injected again to the wells. This was an overview about the process. I hope I could increase your knowledge and tell you something new. And I hope it will be very valuable to you and beneficial for you. If anyone have any question, please say it to me, and I hope I can help you.